יכול להיות אם אנחנו מדברים על אות ריבועי באמת. אוקיי? אז מה זה הדבר הזה בעצם? זה אינטגרל על כל תטא של P של תטא, כפול אינטגרל על כל D של R P של R בהינתן תטא, כפול על לוס הזה. זה הגדרה של ה-MSV. בסדר?
כן, לא, אז עכשיו אני מבין משהו. כאילו, השאר עכשיו כאילו ברור, אבל...
אז זה פשוט, זה שווה לך...
זאת הגדרה בכלל כללית?
זה הגדרה כללית של שנייה. אז זה תטא בהינתן R חלקי PR. PR אתה מעיף אותו בגלל שהוא לא קשור לך, לא תלוי לך בתטא, אז אתה נשאר עם הפי תטא בהינתן R כפול הלוס, ומפה אתה ממשיך.
טוב, עכשיו עוד קצת למה בזכו או ככה, אבל בסדר.
זה הגדרה של דיסטר.
כן.
ובלי שום קשר למה הדיסקרימינטור שלך, פשוט ההגדרה של השנייה.
כן, אוקיי, סבבה. תודה.
הטעתי אותך, תגידי לפני.
לא. סבבה.
אם תגלה שהטעתי אותך, תגידי לפני.
Okay, I'd like to start. Sorry for the delay. Um, Let me remind you what we were talking about last time. So we were talking about linear perceptron. We have some inputs, x1 to xn, and one output unit, y. We're trying to learn some weights, w1 to wn. And what this network is capable of doing is a simple linear computation. Y is equal to the sum of wn xn. And we're trying to learn from examples a function. The function is some general function f of x. Doesn't have to be linear. And we're learning from examples. X mu and y mu. So this is the desired output for x mu, and y mu is equal to f of x mu. Mu going from 1 to t. Here?
No, y equals the sum wi x.
Wi, okay, this is a summation index, so I could use, but n, okay, n I use for this, so thank you. I going from 1 to n. And f of x, well, no, f of x is the function that we want to learn. Y, I use the notation y for the output, the actual output of the network. But this is perhaps a bit confusing in my notation, but I'll stick to what I've done last time. Y mu is a desired output. Okay?
Did you say there is some function
Yes.
of the inputs, and you want to try to write it as a linear function, right?
Approximate it as a linear function. And
But given y mu is given to you?
yes. So in each one of the examples, I'm given a vector and the desired output.
But my question is, what is the motivation to write it as a linear?
Okay, so I will say very briefly, because I discussed this last time, that we want to understand what a simple architecture which is compatible with the type of things that we think neurons can do. What a simple architecture can do. Okay? But if I would say that y can be anything, then I'm not really limiting myself to a specific form of computation. Okay, and the last thing that I should say, that we typically imagine that the inputs are drawn from some distribution, P of x. Why is this important? This is important because if we're going to ask questions about performance of our network, after we learn from some examples, the performance will of course depend on the distribution of x. If x happens to, just as an extreme case, if x happens to be every time just a set of n examples p examples that we've shown, then of course it will work perfectly. But usually we imagine that x comes from a broader distribution, but the form of the distribution might matter. Okay, so now let me just remind you of the results that we got. Last time we saw that if p is larger or equal than n, then the optimal, so we look for weights such that we will minimize the mean square error. Mean square error on the examples. And then what we found that to do this, we should choose weights that have the following form. So when p is larger than n, the optimal weight and I use TR to remind myself that these are weights obtained from a certain set of training examples. So so the optimal weights are written in terms of a matrix C, the vector U, and the matrix C, I will not write explicitly its form, but it's an n by n matrix, and it's the empirical correlation matrix of inputs. By empirical, I mean that it's not the true correlation of inputs derived from the probability, it's the correlation that you can estimate from the examples that you've seen. So it's a correlation in the examples, in the set of examples, and U is the empirical correlation between inputs and the output. So this is a vector. This is an n-dimensional vector. Okay, this is what we got for the case where p is larger than n, and when p is smaller than n, you will go through this example. Did you have already a TA session? Okay, so you went through this example today, right? For p smaller than n, we find that the optimal weight can be written as a sum over the examples, over the example vectors with some coefficient omega mu, plus some other vector which can be chosen arbitrarily. So this represents a degeneracy in the solution. There are many possible solutions. And what this vector obeys is that it is orthogonal to all the x mu's for all the mu's, and such vectors exist because p is smaller than n, right?
I know you explained it in your last lesson, but why do you assume very low probability of getting dependent equations?
Well, you can do show this. I will not do it, but you can show that the probability is really zero. So because once you have a set of constraints on your weights, if you imagine that your weights on your vectors, and you imagine that your vectors are coming, if you imagine that the vectors are coming from a distribution really in the n-dimensional space, which is not concentrated on lines or hyperplanes, of course, you could imagine a distribution of the x mu's which are always dependent on each other, on a lower dimensional space and n-dimensional, and then you will get dependencies between them. But if you assume that the probability distribution P of x is really smooth, is a smooth distribution over the whole n-dimensional space, the probability that you will end up with a set of vectors which are linearly dependent is zero. Because if you calculate it, you'll see that it's the measure of this event is zero.
Yesterday I used Riemann minor as in 2 dimensions, and I got, not for this purpose, but I got Riemann.
So first of all, once you do things on the computer, there is some finite probability that it will happen because the computer has a finite precision. But still, I would like to see what you've done, and maybe, I mean, it's still a bit surprising to me. If you'd really choose a two-dimensional, say 2 points in two-dimensional space randomly using MATLAB. Okay, x component will be round, and y component will be round. The probability that you'll get two vectors which are exactly proportional to each other is extremely small. Okay, so I don't know what happened there, but it's worthwhile looking at it. Okay, in any case, the most, maybe we can talk about it in the Africa. Okay, so the most important thing to note here is that when p is smaller than n, then you have zero error. You can match precisely the output of the network to all the examples. And I think this is more or less where we stopped last week.
Zero error is also p smaller than n, right?
Yes. In fact, for p equal to n, you will still be able to do it. So p equal to n is really, these two cases overlap in a sense. You have n equations with n variables when you try to solve these equations, and you can solve them when p is equal to up to n. So it's worthwhile, maybe it's worthwhile to also to think. I will not do it explicitly, but what fails in this form of solution when p is larger than n, and what fails in this form of solution when p is smaller than n. Okay, in fact, this solution kind of works. The problem is that you cannot invert this matrix. So there are many solutions. Anyway, so. Okay. Now I want to mention a concept. Just to mention it, realizable patterns. So if I give you a set of patterns, set of x mu's, y mu's, this pattern is called realizable if some weights exist, let's call them W0, such that exactly achieve the desired function. In other words, y mu is equal exactly to W0 transpose x mu for all the mu's. And so, just in terms of this, definition, every pattern for p smaller than n, every pattern is realizable for p larger, actually smaller or equal, for p larger than n, typically most patterns are not realizable. But note that there are, of course, patterns which are realizable. For example, if f of x mu is equal to some linear function of the inputs, the function that we try to approximate, let's call this wf x mu, transpose x mu, then of course, whatever number of examples I will try to look at, I will be able to find weights which realize this relationship, and of course the weights are W0 equals Wf, right? So in that case, if we try to follow this strategy for finding the W's, not only we will minimize the error, we will find the true Wf that was underlying the examples. And it's worthwhile to see explicitly that this is in fact what happened.
What is the difference between realizable quantity and zero?
It's the same.
And so why for p larger than n? For p larger than n, we have the inverse matrix?
Yes, but we usually don't get zero error. We get some finite error. So in this example, we get some finite error. We cannot find typically weights that will give us zero error. We just find weights that minimize the error on the examples. Yes?
Did you mean Wf is the same as W training?
Well, there's no we don't have W training. We have we have a W. I'm imagining an example where the function that I'm trying to approximate is a linear function. So with weights that I call Wf. And then I'm saying if I will show you many examples of like this, and you will try to find linear weights that achieve this relationship. If you have more, actually, if you have, you will need n examples in order to find all the weights, but you will find the correct weights. I'm not showing it explicitly. I mean, it makes sense, right? But this will be left as an exercise. Okay, so so in any case, what we looked at so far is what happens when we try to minimize the error over the set of examples that we've seen, but we want some measure that will tell us how well our approximation is doing over a larger set of examples. Remember, we imagined that the examples are coming from a broader distribution P of X, and we've only seen a few examples. So for this reason, we define I don't need to cover what I've just done. I will put this here. We can define something called the generalization error. Which is really the average error over arbitrary examples. Okay, let's write it mathematically. So for a particular set of weights, for a particular choice of the network, we define the generalization error as an integral over all possible x's, weighted by the probability. So here you see explicitly that the P of X is important, and the error for the particular W. Right? Where this, I remind you, this is the difference between W transpose X and f of X squared. Right? Okay, so we can write e.g. this thing. We can write it as the average, and I had a half here just for convenience. I put here a half. It's just a matter of definition. So we can write this as half the average of f of X minus W transpose X squared, and averaged over the distribution of X. And I think that here maybe you cannot see what I wrote here.
Move the bullet.
Yes. But then I don't have space to write. Okay, I will erase it.
Yoav, so f of X is also y0.
Y0?
Yes,
or
that we defined in the TA.
Good. In the
No,
TA.
in
In the TA session. I didn't use the notation Y0 in the class, or if I used it, it was unintentionally because I erased it from my notes. But probably Nathan did use it. Okay. Okay, let's continue. So this is the definition of the generalization error.
But right now you defined as the given samples that we get y mu.
Okay, so you can define, there are two types of error, and this is very, very important. One error is the error on the training set, right? If P is larger than N, we cannot achieve zero error on the training set, and we have some error on the examples that we were showing. This error is a different error. This error is, I showed you the training set, and you optimized for the training set, but I'm asking now what would be the average error if I give you a million examples drawn from the infinite number of examples drawn from the distribution P of X, what would be the average over that distribution? So these are two different things. And this has to do with how well you generalize over a larger set of examples. So what can we say about, so there's e-training, is the error over the examples, and we have e.g., which is the generalization error. what do we expect would be the relationship between them?
Generally or equal.
Which one
P generalization.
is
Smaller.
smaller or larger?
Larger or equal to.
Larger, right? Because we optimize for the example. So of course, we choose a set of weights which will be the best possible for the examples. But if I showed you a different distribution of examples, we expect the error to be larger. So E training is smaller or equal to E generalization. Okay. And
But don't you have any examples?
hmm?
Don't you have any examples?
Yes, yes. Oh wait.
You can have by chance
Smaller and equal. Okay. This is what we expect. I mean, I think there could be some strange situations where this will not happen because you might have some very special examples for which you end up having a large error, whereas most of the examples come from a different distribution. So imagine that this is what we expect, and you can come up with some crazy, strange situations where this will not occur. Imagine that typically your examples come from a set of x's for which a linear relationship holds. Okay, I'm not sure. Actually, I'm not sure. I'm not sure whether this always occurs or not. I need to think about it. But this is certainly what we expect. And now let me tell you some facts which I will not go through the theory, which is interesting, and I will not go through it, but I will talk about learning curves. Let me first explain what they are. So learning curves tell us something about the performance, this generalization error, as a function of the number of examples that we are shown. Of P. None of these. So what I would like to plot is two functions. I would like to look both at EG and at E training as a function of the number of examples that I'm being shown. Let's start with E training because this is something that we discussed explicitly when we optimized the weights. So what can I say about E training? Remember that the behavior for the training we had a different behavior when P was smaller than N and when P was larger than N. What is E training when P is smaller than N? It's 0, right? Our network can achieve exactly the desired output. And
the y-axis is MC. The y-axis and the
yes, the y-axis will be either E training or EG. So right now I'm plotting. I'll use different colors for them. So let's do E training in red. So E training is 0 when P is smaller than N. And what happens when P is larger than N? Typically, we will have a finite error. And when we provide more and more examples, we will approach some limit. Now, what is this limit? This limit, which I will call E min, is the best possible error that you can get if you search for a linear network that will try to minimize the error over the whole distribution of P of X. Right? If I show you an infinite number of examples, then you're really sampling the whole distribution, and then the empirical correlation matrices that appear in the solution for the finite number examples really become the correlation matrices of the input, the true correlation matrices of the input and the correlation between the input and the output. And we end up finding the best possible way that will minimize also the generalization error. So E minimum, but let's explicitly write what E minimum is. So we can think about some optimal weights, let's call them W opt, which are the weights that achieve the minimum generalization error. Okay, so this is an argmin over W. And then E min is the generalization error of W opt.
Aren't you talking about the training error?
We are. But now what I'm saying is that the generalization error is defined as the error for a certain weight set of weights average over the distribution P of X, right? And I'm saying if I'm training over an infinite number of examples which are drawn from this distribution, I will find the weights that will minimize this error. Okay, the reason that I'm not finding this the weight that minimize this error typically is that I show a subset of examples which are not truly represent the distribution P of X precisely. Okay? So this is what happens for each training. Now let's talk about the generalization error. By definition, of what I wrote here, the generalization error will also approach this limit when P is large. But the generalization error will approach this limit from above. When I have a small number of examples, I will have a generalization error which is larger than the best possible one. Generalization error cannot be smaller than this. Okay? And what happens for the generalization error when P is smaller than N? It's not defined. Why is it not defined? Why is the generalization error? Who said that it's not defined? Okay, so why?
I remember it's not defined now.
Because we have a lot of solutions that are
Exactly, because there's no one particular solution. So it's not defined simply because you would have to pick for each one of the possible solutions. There will be a different generalization error.
But then we have one with the minimum.
So it's not obvious that the one which so you could have defined something like this. Pick up from all the possible solutions the one that has the minimal generalization error. And I'm not sure how it will behave, so I will not try to try.
Isn't it obvious that it would be largest because we have less samples and
So I'm saying the generalization error cannot be, by definition, this is the minimal possible value for the generalization error. So generalization error cannot be smaller than this.
no, I'm talking about I'm saying that no matter how you could try to take one W or average over all the from W indicates that P is smaller than N. I expect that the generalization error will be larger.
So first of all,
It will be a decreasing function.
yeah, I think it will be It will be a decreasing function. I'm not sure how it will behave if we choose the one that has the minimal value. But one very important thing to note about both of these curves, that these are statistical curves, right? Because the choice, of course, the actual training error and generalization error for a particular set of weights depend on the P examples that I've shown. So all these curves represent an average, an average over the particular choice of the examples. You could, and by chance, get a set of examples that will give you different values. It's a distribution. But this is the general behavior that is expected, and moreover, I will tell you without showing that it's possible to show under fairly general conditions that when P is large, if we just look at the behavior of these two curves for large P, the generalization error of P behaves like E minimum plus some constant over P, and the training error behaves like E minimum minus some constant over P. Okay, so the approach here is like 1 over P, and it's the same A in both of these expressions. So let me just discuss briefly what are the important questions when we look at a certain network architecture. Here we're looking at a linear network trying to approximate a continuous function, right? What are the important questions that we might want to ask?
Can I have one question? Because about the graph, the generalization error.
Yes.
How does it behave when P is close to N? Does it go to infinity?
So
or
it depends on the situation. So that's why I'm not drawing it.
This is the expression for each, right? Where
Yes.
do you see dependence on the
Well, this is okay. It's important to see that you understand the definition. This is a function simply of a W. For each W, you can ask what is what is this function of W, which is, so I call it generalization error, but it's not explicitly in the way it's defined. It has really nothing to do with generalization. It's a property of a W. For each W, what is the average error, right? I call it generalization error because typically I think of the W as coming from a finite number as optimized for a finite number of examples, and then I want to ask what would be the error for other x's coming from the same distribution, and that's why I'm calling it a generalization error. Okay? So this, by definition here, this is simply a function of W. The reason that it depends here on P is that what I'm really showing you is the following. Do the following experiment. Pick up n examples drawn from the distribution P of x, P examples, not n examples, P examples drawn from the distribution P of x, optimize the weights for this distribution, and then see what is the generalization error, and do this over many times, and this is the average over time. Okay? Okay, so let's ask some questions, or at least mention some important questions. One important question is, what does E mean? For a given architecture, is E mean small enough? Can the architecture typically achieve an error which is small enough for our purposes? This, of course, depends. It's a question about the architecture. But also about f, the function f of x, and about p of x. So the question whether a certain architecture would be able to achieve a small error, of course, depends on what kind of function we're trying to approximate, not only on the architecture itself, and also about the distribution of the examples that we're drawing from. And then there's another question, which is important, and this is, can we find a learning algorithm that will converge to E minimum, and also maybe we might ask if it will converge quickly as a function of P. Okay? This, of course, is also has to do with the typical, the type of functions that we're trying to approximate, the structure of the architecture that we're looking at. But this is a question about the learning algorithm. For example, for the linear network, we've seen an algorithm for learning. The algorithm is optimized the weights simply for the training examples. And it has a certain form of structure, a rate of convergence towards the best possible training error. You might wonder whether there's some other algorithm that will converge more quickly and so on. All these are important and interesting questions. I'm just mentioning them, and they are part. And discussion of these questions is part of a theory that I will not cover in this course, a statistical learning theory. Just mention. At least let's acknowledge that there is a theory about these questions, and that these questions can be formalized, and there are interesting theorems statements that can be made about them. Are you studying these topics at all in עיבוד מידע ולמידה? No? Last year?
No.
Okay. In previous year there was a discussion on this? Okay. Okay, so
There's argument whether we are learning.
okay, there is argument whether there was discussion on this or not. It's at least important to know that there is a deep and very highly developed theory dealing with these questions.
So, can I ask something?
Yes, it's a good time to ask.
Is E min somehow related to asking how close to linear f of x?
In some sense, yes, but you can also imagine that it depends. So, if you're trying to learn a function which is highly nonlinear, but your set of examples are drawn from a small region where you can approximate the function as linear, you will also do
That's
well.
sort of like saying that p is smaller than n. Like if you have, I don't know, I'm missing the because if you have very small amount of examples, you can always fit it.
That's right. So in fact, if p is smaller than n, you're very often going to get solutions which work very well on the examples, but will work very, very badly on other ones. And you can see a hint of this in this curve, which it goes up. And at least for some of the examples, some of the choices here, as we discussed, the generalization area is not defined here. But for some of the choices, it will be very large because you're basically overfitting. You can always find a certain weight that will fit this function, but it doesn't guarantee that it will do well for the other one. Okay, I think this is a good time to take a break.
מקודם,
מוזר, כי נראה כאילו שזה, ולא הלכת לדבר. כאילו, לא ממש דבר כאילו, אבל היה כאילו דולר. אתה ידעת שזה גם
אחד מהם יהיה 0 ואחד מהם יהיה 1, נכון? זה תמיד יהיה או זה או זה, נכון? תלוי לפי מה המצב.
אוקיי.
אז את רוצה שהאסטימטור שלך יהיה כזה שאת תמיד תבחרי את המינימום מבין שניהם, ואז בהכרח אופטימלי.
שכאילו, עבור סשן מסוימת אם זה יותר גדול, אז אני אבחר קטע 2, וזה... נראה לי, זה מה שעשינו עכשיו, היה תרגיל להראות בעיבוד מידע עכשיו שהראינו שזה שווה למין, זה היה למרקר, תרגיל הקודם, שזה היה להראות שזה שווה למין בין רק ששם היה, זה היה להראות שאם אנחנו עושים איזושהי קוסט פונקשן, האמת שזה בדיוק זה.
כן, האמת שכן, עכשיו זה היה כתבו את זה.
הם קראו לזה הראה שכל בייסיאן אסטימטור.
כן, אז
כן.
שבהכרח הכי טוב גם אף אסטימטור,
כן.
למה הם עשו את זה מסובך אם להוסיף אינפורמציה ולא ככה זה די?
לא, כי ככה אני עשיתי את זה, כאילו, ככה עשיתי שם, אפילו אמרתי שאני רוצה לעשות מאיזושהי R, לאיזושהי קראתי לזה, כאילו, איזושהי...
בעיבוד מידע?
לא, כמו על הנוירונים, אבל אני טוענת שזה דומה לשאלה שהייתה בעיבוד מידע.
איזה שאלה?
אבל שככה, שנייה, כי אני רוצה לעשות את זה, ואז זה מה שאני, בדיוק את זה, כפול לקחתי את R, ואז זה בדיוק מה שעשיתי. אני צריכה להסתכל שנייה על השאלה, אני חשבתי בנקודה, אז אולי יהיה...
מה שעשיתי בדיוק לפי הרעיון שלה. זה דבר היחידי שאני
לא, אבל לא ילכו לך לעשות את זה. לא, אני יודעת. הייתה את השאלה על האנטרופיה. אני מסתכלת שנייה בתרגיל, יש לי בצרוק הרי, אני מסתכלת שנייה בתרגיל.
איזה שאלה?
דיברנו על נוירונים על אחד.
ואז הגענו לשאלה.
על אחד, כן.
עשית את זה?
לא, אני לא, אבל אני מסתכלת שנייה, כי נראה לי שזה מתשק, שכאילו, אם מניחים, כאילו הקול שלי, שהיא, כאילו באמת, כן, כן, תגיד את זה לך, היה ממש בזה. אני מסתכלת, אני יכולה לסוגרת, אני לא יודעת.
תראו מפה, את מבקרת מדי פעם, כאן? אני הייתי מבקרת היום קצת המוקדם, לא הייתי מזמין את כל שם, תל אביב. זה הלוויה שלך, מה אלה? מה זה? לא ידעתי. מה? עזרת? כל הספר. לא יודעת למה צריך לחתום על כל דבר את כל ירושלים, אבל... מה, זה פשוט הציבור? כן, היה מחתום, שונה איזה משטרה חברה. ככה זה בא. איזה בעיה ששאלתי את זה קודם, אני מרגישה כמו בכיתה ו'. לא נורא, מה, בטוח יש, כאילו. לא יודעת, זה לא יודעת יותר בנות. לא באמת תהיה כמו. מה, למה אין לא כמו? אני לא רוצה שאני בעונה, אבל לא יודעת. זה היה לנו קרוב לשקל. זה היה לנו קרוב לשקל, זה לא היה שווקת, כאילו לא היה לנו זמן להיות בנופש ביחד, כי כבר הייתה עוד כל יום וידעתי שזה להיות בזמן עם התחילה, זה היה די פתאום ונוכל להגיד שאני חייבת את זה סתם. אבל לא נהנינו, יש כאלה שכאילו ביקשתי שלא רוצה לשאול. זה אפילו שאני שואל מה אתה רק מילה, זה עדיין. לא ידענו מראש את המחירים של השאר, אבל לא פרסמו אותם, כי אנחנו היינו היחידים שהגענו, שבאנו לשלם בודק. באמת? לא, אנחנו, היה לנו שעמדנו בזה, היה לנו איזושהי הערכה שזה
כן, המון זמן, יום שבת. היי, let's take it.
Okay, so we're done with what I wanted to tell you about linear perceptron, and I'm starting to discuss now a very important example for supervised learning, which is the binary perceptron. this topic will this topic will occupy us this week and actually also next week in the context of a variation on this theme, which is the support vector machine. Okay, so the binary perceptron. And so the difference with respect to what I've done previously is that now the function that we're approximating is not a function, is not a continuous function. The inputs are still continuous. Okay? We have x1 up to xn. We're still weighing them using some weights linearly. But then we're generating an output which is equal to the sign of W transpose X. And so the output of the network is a binary output. Either, we'll think about it, it's either plus or minus, it's minus one or one, or you can call it 0 or 1, that doesn't matter. It's a binary output. Yeah, we'll call it -1 or 1. It's a binary output, and we're trying to approximate a binary function, a function which is binary. So we have n inputs which are graded. We have one output, binary. And conceptually or geometrically, we can think about it in the following way. We have an n-dimensional space, coordinates x1 up to xn. Of course, I can draw only 2 of them on the whiteboard. We have some points on space which will be our examples. And we have a certain vector W in this n-dimensional space. And if you think about the question, when is W dot X positive or negative? How can I describe geometrically the positions in space where W dot X is positive versus negative? Plane. Okay, so there's a plane. It's actually a hyperplane, an n-1 dimensional hyperplane. So if we're in 2 dimensions, it's a line. But more generally, it's an n-1 dimensional hyperplane. And we call this a decision surface. On one side of this plane, we will choose +1, and the other side of the plane, of this hyperplane, we will choose -1. This is all that a linear network like this can do. It defines a plane in n-dimensional space and assigns 1 to all the points which are on one side and -1 to all the points on the other side. Okay? Another just word that I would like to mention, if I should have done this before, the function that we're trying to approximate is binary, and this function of this type is called a dichotomy. So for example, on the examples that we will try to learn from, in each one of the examples, the value of the function can be either 1 or -1. It's a dichotomy. So the binary perceptron, a linear separation using a hyperplane in n-dimensional space is perhaps the most simple way, mathematical form, to implement a dichotomy. That's one reason that we're interested in this architecture. It's the most simple mathematical form for implementing a dichotomy. But it's also in line with what we imagine neurons can do. I mentioned this also when we discussed the linear perceptron. We imagine that neurons, but this is really, even with the nonlinearity, this is really the prototypical way we think of neurons when we try to idealize them mathematically as much as possible. We think about them as objects that receive some inputs, they weigh them linearly, and pass the result through a nonlinearity. Okay, so what I would like to discuss now is the capacity of the perceptron. What do I mean by capacity? So we can try to ask for an n-dimensional perceptron, how many functions can it implement? What is the answer?
How many functions?
Mm-hmm.
Can you repeat the question?
Okay, I'd like to ask I will modify my question in a moment, but I would like to first ask, how many functions can a perceptron, an 8-dimensional perceptron, how many different functions can it implement? One?
I'm not sure.
Okay,
that
so
I
a function, by function I mean a binary function. So a function is some binary function of x. X is an n-dimensional variable, and two functions are different if they assign different values to any two x's, right?
Okay, so n minus 1.
So, okay, so we have one suggestion. We had one suggestion which was 1, which we already.
Turn this line in
Yes.
any degree we want.
Yes. So it's infinite. Good. So that's the correct answer. The number of different functions that we can implement is infinite. We can the slightest change in the orientation of this plane will change the function, because points that were previously on one side of the plane will no longer be on that side. So there's an infinite number of functions, so that's not an interesting question.
But it depends on the input, for a given input.
Okay. So instead of asking for general functions of n-dimensional space, how many functions we can implement, that's infinite. We'll ask for a given set of inputs. For p points in Rn, for b given points, how many different functions can be implemented? That's the question that I would like to address.
When you're saying infinite, can you please stop it?
Perfectly. Okay. Now, in contrast to the linear perceptron, where if it's imperfect, we need to decide how we define the performance. We used mean square error, but we could have used other criteria. For the binary function, it's pretty clear how you quantify the performance. It's a number of points over which you give the correct answer. You can give just one of two answers, right? So, but now I'm discussing how many functions can be perfectly, precisely implemented. Now, before we try to answer this question, let's ask a different question. How many functions are there for p points? 2 to the power of p. So, how many functions exist on p points? The answer is 2 to the p. So, of course, we cannot expect. So, the answer to this question will be anything between 0 and 2 to the p.
Why can't we achieve all these two?
Okay, so this is something that we need to discuss. Okay, but we will see. Okay. So really, the question is what fraction of these possible functions can be implemented? And another important comment, if you look at this question, is that in principle, it depends on it might depend on my choice of p points, right? But for the linear perceptron, it turns out that the answer is almost independent on the choice of the points. What do I mean by almost independent? We will need to consider, so let me first consider in our discussion here points which lie on what I will call a general position, which I will define now. So a set of points x alpha in an n-dimensional space, let's mark it again Rn, are said to be in a general position actually, I will write a more precise term, which is general linear position. But people often say simply general position. And this is, from here on, I will simply say general position. And the points are in a general position. I'll write down the definition. Okay, so if I choose n plus 1 points in n-dimensional space, then of course they are linearly dependent because the dimensionality of the space is n. But if I choose n points or smaller randomly in n-dimensional space, usually they will be linearly independent. And this is what I assume about the point of alpha, that any subset of them, if the subset contains n or smaller number of points, these points are not linearly dependent. There is no linear relationship that relates them. Okay? And it turns out, surprisingly, that the answer for this question is the same for any p points which lie on the general position. So this is why so it's going to be a very general answer which is almost independent of the set of points. And before I continue, I will make another definition. I realize now, did everyone get a chance to copy this?
Yes. And when n is bigger than 1.
When, yes. Well, I mean, n points. Okay, so just another definition, just a terminology, a dichotomy on p points, x mu, y mu. Is called linearly separable if W if it can be realized by n minus 1 dimensional hyperplanes that passes through the origin. Or in other words, if there is some W such that y mu is equal to the sign of W transpose x for all. Okay? So this is just another way of saying implemented. Can be implemented. Can be implemented by binary perceptron is what we call linear linearly separable. Okay, so now we come to a very important theorem. What's that? Now we come to a very important theorem, Cover's theorem. And this is T.M. Cover, the same Thomas Cover from the book Cover and Thomas on information theory that I mentioned to you. And this is from 1965. So Cover obtained an exact answer. What is the number of linearly separable dichotomies in n dimensions on a set of points which lie on a general position? So the number, okay, we write it down, the number of linearly separable dichotomies over on a set of P points in a general position in n-dimensional space. Actually, instead of n-dimensional space, let's just write Rn. Is equal to, now comes the formula. Okay. So P minus 1 over K is the number of possible ways to pick K objects from a set of P minus 1 objects. And note here that the sum here, depending on whether n is larger or smaller than P, if n is larger than P, we might have here cases where the number written here is larger than the number written here. Okay, so just by definition, m over n is 0 if n is larger than n. Okay? I'm trying to pick up more objects than the number of objects that I have. It makes sense that I want to define as the number of possibilities to do this is 0. Okay, if m is equal to n, then this is equal to 1. There's just precisely one way to pick m objects from m objects. And one remarkable thing about Cover's theorem is that, as I mentioned, it's not a statistical statement. It's true, this is a precise number for any set of P points which lie in a general position. And the proof will be done by Neta. Let's just look at very simple examples to get some feeling and see that this result makes sense. So let's think about 2 dimensions. X1 and X2. Okay, let's start with P equals 1. When P is equals many dichotomies can we implement? Two, right? We can pass the plane on either side of the point. So we can set the function to over the point is either -1 or 1. And using this formula, we have 2 times sum over k going from 0 to 1, right? N minus 1 is 1. And we need here p minus 1, which is 0 over k. So we'll get a contribution only from k equals 0. 0 from 0, that will give us 1. So it's 2 times 0 over 0, which is equal to 2. What happens if I take p equal to 2? So let's add another point. Now how many dichotomies can I implement? 4. I can still implement all the possible dichotomies. I can pass the plane such that both points will have the same value, or I can pass it between them and they will have different values. So I can still implement all the 4s, and if I look at this formula, we have 2 times. So now p is equal to 2, so I write here 1, and I have the case k equals 0, and I also have the case 1 over 1. Both of these numbers are 1, so I get indeed 4. And now let's take a case where I add a third point. And this case is the first one where we can see a situation where I cannot implement all the possible dichotomies. Because imagine that I pass the plane here. I can either make 2 of the points have one value and 1 of the points have a different value, or these 2 points have the same value on this point, but I cannot make, in this example, all 3 points have the same value. Whichever way I choose the position of the plane, 1 point will be on the one side of the plane and 2 points will be on the other one, right? So the number of dichotomies that I can implement, okay, so what is it? So I have 3 ways to choose which one of my points will be the special one, right? But I can choose the sign of the weights either way, so I can make either one of the, so one point will have value 1 and the 2 others will have -1. I can choose each way. So I have 6 possible functions that I can implement, right? By the way, I could have chosen the third point to be here, and in that case, I would have a possibility to have the 3 points have the same value. But you can go over this example and convince yourself that in that case too, I will have only 6 functions that I can implement. But let's follow this example. So I know that I have 6 possible functions, and let's just see that it exists it agrees with this expression. So I have here 2 times 2 over 0 plus 2 over 1 plus 2 over 2. This is equal to 1. This is equal to 2. No, something is wrong here. K goes from 0 to k minus 1, n is still, okay, here it's still 1. Okay, so I have 1, 0, and n is the dimensionality, right? So k goes from, no. So I have here p is equal to 3, so it's 2 over 0. And 2 over 1. Thank you. Because n is equal to 2, so I only go up to 2 over 1. So this is 1. This is 2. I have 3 times 2, and it's 6. Good. Okay. So after these simple examples, what I want to do is to discuss how this expression looks like when n is very large, when the dimensionality of the space is large. first discuss what happens when p is smaller than n. Okay? When p is smaller than n, then Cp of n is equal to the sum, to 2 times the sum, p minus 1 over k, and k goes from 0 to n minus 1, but because p is smaller than n, I actually cover all the values, all the possible values up to p1 minus 1, and the rest are 0. Right? But what is this? Does anyone know what this sum is equal to? Okay, this is really the expansion, for the binomial expansion for 1 plus 1 to the power p minus 1. So the 2 is this that I'm writing is this 2. But if I would write the binomial expansion for this thing, I will get a sum over all possible powers going from 0 to p minus 1. This coefficient, which tells me whether I'm choosing this term and this one term, and then this is 1 to some power and another 1 to the same power. So the ones don't matter in this case, right? And this is equal to this. So I'm getting 2 times 2 to the power p minus 1, and this is 2 to the p. What does this mean? That all the possible functions can be implemented on a general position. And by the way, this statement does not depend on the fact that n is large. This is true for any n, but my goal is to discuss the behavior for large n, and you'll see where this matters later on. Okay, now let's look at another very special example, and this is p equal to 2n. You will see in a moment why I'm picking up this example. Okay, so in this case, Cp of n is equal to 2 times sum k going from 0 to 2 times p minus 1. Okay, so let's write it for now as n minus 1. P I will write as 2n. Okay, so I write here 2n minus 1 over k. Right? So I have here k terms. I have here n terms. Oh, I don't. Is this still visible? I have here n terms, 0, 1, up to n minus 1. And I want to rewrite this a little bit differently. So I claim that this is equal to 2 times half times the sum where k is going from 0 not now to n minus 1, but I will go now up to 2n minus 1. Okay, and why am I doing this? Why am I saying that this is equal to this? So note that here I have 2n terms, 0 up to 1 up to n minus 1, and then n up to 2n minus 1. But I claim that each one of these terms in this set has a matching term in this set which is exactly the same, because remember, when we write m over n, on the denominator we have, or n over n, when the denominator we have n prime and n minus n prime. So for example, this term will be the same as this term will be the same as the next one, and this term will be the same as this term. This is why I can write this. But now, in this expression, you see that this is it has the same form as what we had here. We're running over all possible powers up to 2n minus 1. So this is 2 times half times 1 plus 1 to the power 2n minus 1, right? So what I'm getting, the 2 cancels this, I'm getting 2 to the power 2n minus 1, which is also half times 2 to the p, right? Because p was 2n, right? So what did I get? What I got is that when p is equal to 2n, exactly half of the dichotomies can be implemented. Okay? And finally, let's discuss what is the behavior when p is much larger than n. This is where I'm going to really assume that n is large. So I claim that CPN, okay, I erased the expression for CPN, so let's write it down. BPN is equal to the sum over k going from 0 to n minus 1, p minus 1 over k. And there's a 2. So qualitatively, CPN grows as p to CPN grows as p to the power n. Why? Because the largest term that we have here, right? I mean, all the powers that we have in the numerator, we have things like p minus 1 to the power n. Then it's divided by something. But qualitatively, CPN grows as p to the n. And what I claim is that p to the n is much smaller than 2 to the power p. Why do I say this? Let's take the log of these two expressions. Okay, so logs are never large numbers. Logs are what matters here is that n is much smaller. We assume that p is much larger than n. Okay? So the log, this thing is much larger than this, and of course when we take the exponent, it's hugely larger. So for p much larger than n, my main point is that CPN is much, much smaller than 2 to the p. Okay, so CPN is much, much smaller than 2 to the p, and therefore only a tiny fraction of dichotomies are linearly separable.
How do we know that it grows by p power n?
Because you have to just write down what this is. And you have here n terms, right? Each one of them has in the numerator p to the n, or more precisely, p, p minus 1 to the power k, but the large That's the form of the growth. So, so now let's just see what all this means when n is large. So suppose that instead of looking at CPN, I look at the fraction of linearly separable dichotomy. So I look at CPN divided by 2 to the p. And I look at this as a function of p. Okay? So what do I know? I know that there are two special numbers. What is this fraction when p is smaller than n? It's 1, right? All the... So this is precise. Always, for any n, this fraction is 1. I also know something about this point. What do I know? It's half, right? So I know that this function passes through half.
P over n.
That's p over n. That's right. So, yes. So I'm plotting it as a function of the number of levels divided by the dimensionality of the space. And I know that for large n, it's 0, basically. So how can it look like? It look like some function that goes like this, right? But as n becomes larger and larger, this statement that the fraction is tiny becomes precise for values which are closer and closer to 2. I'm not proving it now. Okay, but so when n is becoming larger and larger, even if p is slightly larger than n, relatively, you will already get a tiny fraction. So when n becomes very large, what happens to this function is that it essentially becomes a step function. So this would be, so the black line was for some n1, and the green line is for some n2, which is larger than n1. Okay? And as n approaches infinity, this function approaches precisely a step function. Meaning that, again, for large n, essentially the result is that all the fraction of separable dichotomies approaches 1 as n goes to infinity for p over n smaller than 2, and it approaches 0 for p over n larger than 2 as n goes to infinity, and it's always equal to half for p over n equal to 2. So essentially, again, for large n, you can implement any dichotomy if the dimensionality of the space is the number of examples is up to 2 times the dimensionality of the space. And in that sense, we say that the capacity of the binary pair syndrome is 2 times n, 2 times the dimensionality of the space. And you can essentially implement none of them, or a subset of measure 0 if the number of examples is larger than n, than 2n.
Does it go to 0 or some
It goes to 0. It goes to 0. So the fraction of implementable dichotomies becomes 0 when n goes to infinity. Now, you can think about this result as saying, suppose that you would draw randomly P examples. What I mean by P examples, you draw randomly a function. So the P, as we discussed, and the position of the points doesn't really matter if they are in general position. But suppose that we have P points, and suppose that I draw randomly a certain number of T functions, and I try to implement them. What is the probability that I will manage to implement all of them? So if P is smaller than 2n, the probability is 1. If P is larger than 2n, the probability is 0. One thing to note, though, that I assume here that I draw the functions completely randomly, independently, so that all functions are equally likely. This statement would not be true if there would be some special structure in the functions. For example, if the functions tend to be such that points which are nearby to each other in space tend to have the same value, then the probability that I would manage to implement a function that I draw from such a distribution might be higher than 0, even if P is larger than 2n. So it's always important to remember that probabilistic statements about implementability depend on the space of functions that you're trying to implement. If I try to implement a linearly separable function, I will always manage to implement it. Okay? But for random functions, if I choose my point that values of a function completely randomly and independent of each other, then the probability of success is either, for large n, is either 1 or 0, depending on the number of examples.
Successive number of is the dichotomy that
Success
is
means
without error.
Exactly. Yes. Success, I mean here that I can find a weight that will implement the dichotomy precisely. Yes.
Is there a way for functions that can be divided to be transformed into functions that can be divided? Not functions, but for example.
Well, in some sense, we will see this in the context of support vector machines. We will see some tricks that allow us to take functions which... So when we discuss next week support vector